Hello, students. This is the second lecture this week for Module 1, and I'll be talking about orogenesis, and it ties in with the introduction to geology. And the genesis that I'm talking about is how ore is formed and whether it undergo through one formation or it can be several. And hence, in the assignments this week, I refer to alpha genesis, which might be the first step in which rock was formed, and then subsequent steps, hence beta genesis, and then delta genesis, and so on. I'm only asking you in the assignments to come up with the first two possible processes of ore formation, alpha and beta. The reason this is important is the more you know orogenesis, or know to be able to discuss with subordinates, so you might supervise someday geologists and mining engineers and other professionals in doing an exploration program. You'll be if the team can talk together on the exploration plan and the results of exploration, what ore there is in the ground to exploit, to extract, the whole project will become more successful. The classification of ore deposits, as you've already discovered in reading from the manual, is our 10 basic shapes, and I've offered a classification system by those diagrams in the handbook, shapes. Now, due to geologic variability, there's no universal classification system that exists. And it's because of the variability of geology. That's why we as geoscience professionals we have to be good because we deal with a variable media. Both the classification of ore deposits and the genesis of ore deposits is driven by the rock cycle, which is this. All rock starts with magma, molten rock, and it can either go and become sediment through the processes of deposition, sedimentation, or cementation, dehydration, weathering, erosion, etc. Or it can go and crystallize and become igneous rock. And this process is through melting and cooling and solidification, and very important, crystallization, which we'll be talking about in a minute. Now, all rock can be subject to structural deformation. The structural deformation is mainly three components: seismic deformation. There's a little white out here on the slide, I don't know why, and that is tectonic deformation or mountain building, seismic deformation, which mainly occurs during the acceleration and deacceleration of seismic energy rather than during the constant velocity stage of movement. And we'll be studying geologic waveforms briefly in this course. Also, there can be gravitational deformation, which mainly stems from the difference in deposition, the difference in density of two rock types. Rock can vary in weight, in unit weight, i.e. density, from a little bit more than water, 60 to 70 pounds per cubic foot, up to a specific gravity of 4 or more, which would be 300 pounds per cubic foot. Some other processes, the sediment can become congealed and become actually a solid rock. And at that point, it's called sedimentary rock. And the processes that make that available are consolidation, cementation, recrystallization, dehydration, erosion, and then gravity compaction and consolidation, and then evaporation and lithification. At that point, sedimentary rock, and it can go back and forth, can become metamorphic rock, and then metamorphic rock can become weathered and go back to being sedimentary rock, or metamorphic rock can become loose sediment. It can be remelted and go up and rejoin the phase of being magma. And then, of course, igneous rock can be metamorphized through heat and pressure and geochemical reactivity and become metamorphic rock. Now, this geochemical activity, that's really chemical energy. So there's 3 forms of energy that rock is subjected to, which is heat, pressure, and chemical reaction. And of course, a chemical reaction is measured by the kinetics of the reaction, how fast and how many moles, if you please, are created per unit of time from the left side of the reaction to the right side and back to the left side, the kinetics of the reaction. There's a principle, an overlying principle of mineral genesis, and it has to do with the phase rule. The phase rule is a general way to characterize physics and reactions in physics and media. And that says that the number of phases of a system plus the number of degrees of freedom equals the number of components plus 2. And when this genesis, when this phase rule is applied to the subject of mineral genesis, some principles are done in applying this principle. 1, the chemical complexity drives the number of minerals in the rock. And 2, the degrees of freedom in geology are mainly 3: the bulk composition, temperature, and pressure. And because temperature and pressure are variable, they actually form a constant of 2 in a state of the geologic system. And that's because at any point in time, the temperature and the pressure of that system in equilibrium are constant, even though during the formation stage, they can vary. Temperature and pressure can vary, but the bulk composition during formation doesn't vary. So therefore, the equation for geology can be simplified to P is equal to C, and which is the mineralogical phase rule. And it says, in a system of n components at arbitrary pressure and temperature, the maximum number of mutually stable minerals does not exceed n, or the number of original components of the bulk composition. And we will go through some examples in the next slides for each type of rock. For a system of 1 component, and the major rock type or mineral type is silicon dioxide. It's a one component system. Note that the Earth's crust is 46.6% oxygen and 27% 0.7% silicon. And when that one component is found in rock, you'll only find silicon dioxide. So the mineral phase rule is obeyed. For a two component system, such as two mineral compounds or components of sodium, aluminum, and silicon, and then silicon dioxide, this is a very common two component system during formation, you'll only find two minerals after the formation in the rock. And in this, some examples of a two component system derived formation is nepheline, quartz, albite, and jadeite. For a three component system, a very common one would be manganese and oxygen, and aluminum oxide, and silicon dioxide, a three component system. And when those three enter the formation stage, there's only three primarily minerals that will be in the final rock type. So examples that are ultra-basic rocks and metamorphized shales. And the term ultra-basic refers to original rock, igneous rock. And remember the three descriptions of rock. Igneous rock is original rock. Metamorphic rock is changed rock. And sedimentary rock is weathered rock. Let's go through some details of the genesis of the three different types of general rock. First of all, igneous rock. The main two types of ore are pegmatites and hydrothermal deposits. Pegmatites occur from the residual direct melt of magma and crystallization of magma, which results in silica-rich minerals. So it makes sense that silicon dioxide is a main component of magma. So when it crystallizes as magma would be expressed through the crust, it would have silicaceous rich minerals. The second type of genesis of igneous rock is hydrothermal deposits, and that occurs from development of pegmatites from cooler direct solutions of magma. And a pegmatite is an intrusive igneous rock. Other types of intrusions are called batholiths and latholiths, where an igneous rock has already crystallized, but then as a large unit, it's thrust up through the crust of the earth. And the solutions in hydrothermal deposits, where around the fringes of the pegmatites can either be shaped like veins, small veins, or widely disseminated porphyry deposits, such as the great deposits in Arizona, Utah, and Nevada, and other places in the world over a large area. Metamorphic genesis is, first of all, metamorphism is the sum of heat and pressure and also chemical processes that work below the zone of weathering, causing rock recrystallization. So if a rock on the surface is weathered, it becomes a sediment and can become usually sedimentary rock. So metamorphism is below the zone of weathering in the ground, and it causes recrystallization of the rock mass. There's two contacts of 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 or two types of metamorphism: thermal or contact metamorphism and regional metamorphism. Contact metamorphism occurs at the contact zone in proximity to intrusive magma or granite. And the contact zone can range from a few feet of thickness to thousands of feet. And the intrusive that creates this contact zone of metamorphism can be into all three rock types. And it can be sulfides, iron oxides are examples. The other type of metamorphic genesis is regional. It can occur at the base of Precambrian rock and also at the base of fold mountains, where there's the potential of great heat and pressure that is causing the folding to occur above it, i.e. tectonic force. And finally, sedimentary genesis. Sedimentary genesis is all about sedimentation, and it is the interaction of conditions of the atmosphere and hydrosphere, i.e. the hydrologic regime in the ground of the crust of the earth. And the sediments are down below here, but I want to first talk about a characteristic of sedimentation. We said that how silica, silicaceous material, is a large component of the earth crust. Well, if the strength of the silicate linkage to its surrounding rock increases, the resistance to attack by the sedimentary processes increases as well. So the conclusion of that is that sedimentation can generally occurs in weaker bonded silicaceous material. The sediments are labeled the types of sediments and also denotes their genesis. Can be a resistate sediment, which is mainly composed of quartz, i.e. the silicon dioxide that quartz is composed of. It resists decomposition. The hydrosilates, which makes sense. An example of that would be clays. Oxides, which would be an iron oxide mineral. Reducates, which is a reduction chemical reaction, coal and petroleum. Precipitates, be calcite, or the precipitate action of sedimentation. And finally, evaporates. An example of that is trona, or calcium carbonate, which a lot of the world's supply of calcium carbonate is mined in Sweetwater, Wyoming County. Sweetwater County, it's in the southwestern corner of Wyoming. I wanted to bring your attention to an acronym that's always helped me to remember basic chemistry and reactivity. Oil rig. An oxidation chemical reaction is the loss of electrons, and a reduction equation is the gain of electrons. Hence oil rig, oxidation or reduction. And many geologic processes, and also mitigating the mining impact to the environment, amounts to recognizing whether the reaction is an oxidation reaction or a reduction reaction. Well, that concludes this lecture. I hope this gives a good introduction for a further introduction for Module 1. And please feel free to contact me during office hours or email me anytime or call me anytime. And I'm here to help. I'm here to assist that you succeed in your endeavor, in your career. Thank you.